Okay, quick engineering moment. You see on the right-hand side here, this website from Omega. We're going to talk a little about thermocouples. We talked about these in heat and mass last year, but I want to remind you, if you ever have a question about how accurate a thermocouple is or how to select a thermocouple. Omega is a company. It's one of the big companies that sells a lot of diagnostic things that we buy things from, the company we buy a lot of stuff from. You go to technical reference on the top, and then you can see all sorts of stuff, pressure, strain, force stuff. At the bottom, you have temperature related. Notice that you've got thermocouple tutorials and things like that. That is how do thermocouples work? Let's just remind you what a thermocouple is. There's two types of wire, two different metals of wire. And whenever you put two metals together, they induce a small little voltage. It's called the Seebeck effect or Seebeck effect. I can't remember exactly what it is. But that voltage in the millivolt range is a function of temperature. And so you go ahead and you put these two together, and you can read out the millivolts and then change that over to whatever temperature you want. Now, if you go down here, what are the accuracies of thermocouples? You can see there's different types of thermocouples, J, K, T, E. We have a lot of type K. They're really robust. They have a pretty wide temperature range, you can see. But you'll notice that the error is about a little more than 2 degrees, plus or minus 2 degrees on a type K thermocouple. That's the normal error. Now, the error comes when it says standard limits of error. When you make these, there's just imperfections in the metal that's been drawn or whatever, things like that. And then they test to make sure the resistance and the voltage are correct. And so a standard one is about 2 degrees correct. If you spend a little more money, you can get about 1 degree accuracy. And you can always go in and actually calibrate an individual thermocouple yourself. So you can stick it up to a voltmeter, and then you can stick it into a reference temperature, something of known temperature, maybe with a thermometer. And then you can get the voltage to temperature range yourself, but it just takes time and effort to do that. So if you buy one off the shelf, the best you can do from a normal one is 2 degrees. If you get the more expensive ones, you can get 1 degree. Type T, which is copper and constantine. So notice that these are the two different types of metals. One's copper, one's this copper nickel alloy. Type Ks are nickel chromium and nickel aluminum. But you can see type Ks are a little more accurate. Type Ks usually have blue housings, so you can identify them. And those are the ones you have on the airflow experiment because we want a little more accuracy with our temperature measurements. But what if you want even more accurate than a thermocouple? Someone tell me anyone know of any other ways we can measure temperature to be more accurate?
You could use a thermometer that the level is measured by a laser.
Okay, so yeah, you could. So you're talking a visual thermometer and then somehow measure the level optically.
Yeah.
Thermometers are probably the most accurate things in general. And the difficulty like that is that it's not an electrical signal. So you have to have some sort of optical, either manual or some sort of machine vision type thing. Anyone know of any other types of temperature measurement devices? There are things called RTDs, resistance temperature device, or thermistors. RTDs, instead of measuring voltage, you measure resistance. They're a little more accurate, but they're more expensive and they're a little more delicate. And so you can see that the errors are a little better on these. Thermistors also kind of work on resistance, but they're very, very delicate. They're usually made out of ceramics or silicon, and they want to be in an environment that's not going to get hurt or things like that. They're often used in your refrigerators when you replace a temperature probe. A lot of those are thermistors in your refrigerators to really get accurate. You can see you can get to plus or minus 0.2 degrees. But again, these are ones where you want an electrical signal out, and you can always calibrate them yourself to get more accuracy. But you just want to take that into account as you go and look at data. The temperature measurements are going to be bouncing around. In fact, all the measurements are, because there's an accuracy associated with each of them. The video from the airflow has the tags on the back of all the important equipment, so you can go into the manufacturer specs and see what the errors are on each one of those meters. So any questions on that quick little thing? Okay. First thing we're going to do today is go over your, let's see, go over some writing. I only have about 6 of them to do. I'm going to bring up the text from the emails you sent. And then I'm also going to bring up the slide that was made. And we're going to go through these, and you kind of pretend that you're the boss. Let's talk about whether you think the writing is good. Does the communication work? So go ahead and just spend a minute, read the text, look at the slide, and tell me what you think. We'll discuss this. Okay, so someone tell me what they think about this. Topic sentence, does it flow? Does it get the main points across? Are there confusing parts? Does the slide, do you wonder why things are on the slide? Or does the slide work? Any comments?
On the proposal line, they're saying that they want to find the best method to determine which flow meter, when I think they were just asking us to figure out which is the best flow meter.
Okay, yeah, so there's a little wordy issue here. You could maybe simplify this. You could say the objective of this proposal is to describe the method to determine which flow meter we should use, or which flow meter is more accurate, or something like that. Any other thoughts? Can you follow the slide? Do you know why everything's there?
I think it might help just to mention the different types of meters they'll be using. That way it explains what's on the slide.
Yeah, I think so too. So somewhere in here, if it said something like, we have 3 obstruction meters, a pitot tube, and then a rotometer to choose from, or something like that. And the slide contains the equations to evaluate the flow from the pressure drops for each one of those meters. And then you'll notice that in each one of these equations there is a discharge coefficient. So if you go over here, this equation's a little weird, because why don't you need y and c in this equation? Someone tell me that.
Aren't they both correction factors? So they can be combined?
So just combine them. You're going to get data. You're going to get delta P and T to get rho. So you get all the data you need here. You got a flow meter to give you Q. And so just combine those two. Just call it a discharge coefficient, similar to what you got here. In fact, this equation is kind of technically correct, but it's hard to see the relationship between this and then this and then this Q and this Q, because they're all different Qs. I think you can simplify this equation by the pitot tube. Really, you could cast this in terms of a Q also. And then by putting in M's and A's and things like that, you could then put the CD in here. And you'll notice that if you do that, this equation is the same as this equation. Does everyone see that the pitot tube equation is basically the same as the obstruction meter equation if you put it in terms of Q? So really only have one equation for pitot tube and obstruction meters, and then the rotometer equation. The rotometer equation can also have a CD in here. And so it's kind of all the same thing there. And so you could simplify, I think, the slide by getting really deliberate and getting rid of the Y, because I don't think it's needed, just putting the C in. And then I do like this. They kind of tell you a little method, right, from the slope of the experimental data. But you want to say something like, we measure what our apparatus can measure. We can measure Q real, or what we call our flow meter data. And then Q calculated comes from the delta P stuff. We can measure that. And then we can get a CD from the slope. Any other comments on that?
I guess this is self-serving, so I know what to do better in my equation. But how will they know the real CD per se? So they know which one's the closest to that line.
You're going to calculate CD for every meter. And you don't really care what the value of CD is as long as you have calibrated it correctly. Does that answer your question? I'm not sure I understand it.
Well, their last sentence says the meter with the slope closest to the actual rates is the most accurate.
Oh, yeah.
So
I don't think this is actually correct, because all obstruction meters, or all meters, will have some sort of discharge coefficient. I think what you want to say is, once we have the data, we'll be able to determine which flow meter we want to use. It's not really related to CD. It'll be related to kind of your average error across your range, or your R squared, or however you're going to determine the error. But I think you can leave that a little open and just say, once we have the best CD values for each meter, we can evaluate the accuracy across the flow rates and determine which meter we want. Does that make sense? Let's go to the next one and see if there's any different way that these authors have kind of shared it. Okay. What are your thoughts on this?
Isn't it always kind of implied you're going to use statistical analysis and calibration to solve things? I was wondering if it's just saying that's kind of redundant.
I don't think the topic sentence is that great. I think it can be improved. How could you improve it? I think the one thing I'm missing is it's a little abrupt. You might want to say something like, you asked us, or the goal of this proposal is to, or the goal of this work is to select an appropriate flow meter for airflow applications in our new plant. We have 5 candidates: a rotometer, right, 3 obstruction meters, and a pitot tube, or something like that. Then you can say, the first thing we need to do is calibrate each of these, and then we can assess the accuracy of each. So I think if you kind of get those ideas through, then I think it starts telling a better story. What about,
I think the last sentence is a little wordy.
Yeah, and it's not exactly what we were asked to do, right? We were asked to find the most accurate one, not necessarily make a cost recommendation.
yeah, you don't necessarily need to make a cost. So it's a little different than what was asked for. I'm more worried about, it kind of seems like each one of these sentences it doesn't flow very well. I don't see why one's connected to the other. I don't see why I'm talking about, I don't see why this information was presented, I guess, when it was. I think what you want to do is somehow, like we say, you know, we need to tell you what flow meter is the best, and then there's 5 different ones. To do that, we've put them all in a apparatus that allows us to measure the delta P's and temperatures across each meter so that we can get a discharge coefficient. And then you might want to say something about, right, these meters are governed by Bernoulli's equation as seen on the slide. And then you can start kind of getting to the slide and then kind of describing what's on the slide. Now, on the slide, there's a little thing that I find hard to follow is I don't see how this really fits in because I haven't been told I'm measuring delta P's or I'm measuring T's to get densities. And this really isn't in the form of the equation that maybe the last one was. You kind of want it to be in this type of form. Now you want to rearrange it so that you got what you measure on one side and then what you measure from the flow meter on the other side. That tells a better story because I don't see, right, there's no Q actual or Q ideal in the Bernoulli's equation as it's presented here. So it's hard to follow this logic. Does that make sense? Or any other comments on that? Am I off base? Someone tell me, are you guys asleep?
No, that seems pretty reasonable.
Yeah, I agree.
Okay, same slide. Let's see how the writing's a little different. So the same type of things we've already talked about with the slide apply here, but tell me about the text.
Similar sort of deal with the topic sentence. It's answering a question that we weren't really asked to answer.
Yeah, so it goes a little beyond. I don't know if I'd really care about that, but
yeah.
It connects the ideas together.
Yeah, I mean,
it's
I
weird.
think it gets the big point across in the sense that determine which type of flow meter would be best to implement in our plant. And you could probably just kind of stop right there, right? You don't necessarily need to put right here or determine which type of flow meter is most accurate so it can be placed in our plant or something like that. And I don't really care if you also say eventually someone's going to consider cost, right? You can't just, whether it's you or another team, I don't mind if you put a little cost stuff in there. But my big issue is the connection between the first and second sentence. Why would I kind of say that? What would you like to see next to keep the flow nice?
I don't like the back-to-back in order to start the sentences.
Yeah, that's a little weird. I know Word doesn't like in order to generally, but we use in order to a lot in technical writing. But you probably don't want to start it the same in both sentences. My big thing is you haven't really told me anything about what meters you have. I think it'd be good to say either here in the text or on the slide that we've got, pitot tube, rotometer, venturi, nozzle, and obstruction, or what am I saying? Orifice. And then in order to we plan to gather data, temperature, and pressure across each meter. Okay, I like this. This is important stuff. It's got to be somewhere in. But then when you say we'll use different forms of the Bernoulli equation to calculate the flow rate, and then compare it to the calculated flow rate with the actual flow rate, this is all a little difficult to see, I think, in the short text. Somehow I think you want to use this space in your text to get the reader to the slide, and then make sure the slide really clearly says kind of what we measure, right? T's and P's. That goes into the right-hand side of these obstruction meter equations. What we measure from the flow meter goes into the left-hand side, and then we can get a C from the ratio of those two or the slope of those lines, something like that. Does that make sense? I think this is fairly general. You can get way more specific if you construct your slide better. Okay, got a little different one here. Okay. What are your thoughts here? Start with the topic sentence, and then we can go from there. Who's going to be brave? Who tells me? Who do you think about the topic sentence?
I do like how they mention what types of equipment they will be working with.
Yeah, I would just go in
Yeah.
here and finish it off, right? It's only 2 more words. Get rid of the EG,
Yeah.
get rid of the et cetera, put them all in.
Yeah. And maybe it's just the way I approached writing it versus the way other people have chosen to do it. But I don't know why they would start by saying, you know, given a system, right? I think you just start by saying the system we have or whatever. It's, at this point, it sounds kind of like theoretical, you know, like if we had a system with this, is what we'd do, as opposed to like we do have this system.
Yeah, if I was grading this, I think you could be more direct. And if you were grading just the topic sentence, this would probably be like an A- or B+, because it's got the big ideas, but it's a little wordy or a little awkward. You could just be more direct if you said, you asked us to choose between an orifice, nozzle, venturi, meter, da-da-da-da-da. Or you asked us to calibrate this for airflow and then select which one is most accurate, something like that. I think you could just be a little more concise there and more direct. There's a little bit, you know, since we've seen a couple of these, there's a little bit of a logic issue here. Jumping from here to here, you might want to say something like, instead of say to accomplish this task, you want to say, calibration of these meters requires measuring the pressure drop across each at various flow rates and then calculating a discharge coefficient. To do this, we have an apparatus in the lab where each of the meters is found in series. And we can measure the pressure drops and temperatures along the whole system. And then if you kind of get that, man, that tells me a lot, right? It tells me the purpose, it tells me something about the theory, and it tells me something about the apparatus, and it kind of flows well. And then you can start trying to get people over to the slide and you say, once you have pressure drops, you can use Bernoulli's equation to calculate a theoretical flow rate through the meters. We can compare that to the actual or real flow rate calculated from or obtained from the flow meter, and the ratio of those two is the discharge coefficient or something like that. So tell me some good things about the slide that you like, and maybe some things that you don't like.
I guess if you were writing up the equation, you could just already insert your correction factor instead of saying there will be a factor here.
Yeah, I would definitely stick that in here. Get the C in here. I don't know if that's a picture, but you can put the C in there. And the other nice thing here is well, these are kind of nitpicky, but you don't want to call this ideal volumetric flow rate. You probably want to call this, in terms of the communication, you want to say Q from flow meter, and then pressure at point 1 and point 2, and then maybe put parentheses measured, and then from measured pressure and temperature for the density. That just links, right? Measured stuff. And then it makes sense, right? I got measured stuff over here, measured stuff over here. And then if you say something about, right, we fit the data or use the slope or whatever, then things make a little more sense. So I think you can just be a little, make sure it's really clear where everything comes from. I do like that there's kind of this overall goal. I think you could be a little less wordy or use bullets or something like that, right? Just say, you know, the purpose or overall goal is to calibrate the flow meters and determine accuracy. And then second bullet, method or approach will be measure pressures and temperatures and correlate to Bernoulli's equation. And then it kind of just gives some reference points for the people. It also, you can use those same bullet points. If you use kind of the same wording over here, it gives someone a link to where they should look on the slide. Any other thoughts on this one? So I just copied this straight from the email, and I know there's all these weird little things. I think it kind of gives you an idea on why it's useful to have a slide. Sometimes when you're writing equations or stuff inside, there's weird things that happen, and it's hard to follow. So that's the use of the slide, but let's go ahead and read through this. Okay, thoughts on this? Besides the obvious weirdness of what happens when you try to paste things and it sends across the internet, things like that.
I guess I feel like I'm bringing this up often, but it seems they just expanded the scope of the question a little bit, which isn't necessarily wrong or anything, but I just don't know if we need to do that.
Yeah, down at the bottom, this, you know, the topic sentence, this is pretty, this is pretty close to what we asked, right? Calibrate and what's accurate. I think we kind of say the same thing we've said before. You might want to say somewhere either on the slide or in the text what meters you have, and that the obstruction meters are governed by Bernoulli's equation. That kind of is a logical thing that happens. But I do kind of like it. It says, you know, the first step is to calibrate the flow meters and by finding a discharge coefficient. And then, you know, it says a little about here, you can put this on the slide if you want to simplify your text, but you might want to say finding a discharge coefficient by comparing flow rates measured from a flow meter to the Bernoulli equation to get a CD value. And if you kind of back that up with your slide where you say, here's Bernoulli's equation, this is the flow meter, this is the measurements around the obstruction meters, and then we can get a CD, then I think it starts to flow a little better. I think you see here, the nice thing about having a slide is that things don't get messed up in transit, and they also are a little easier documented. Sometimes it's hard to see equations. This idea is, I know I've seen this in several, theoretical flows versus actual flows. That's always a little nebulous, right? I think everyone kind of knows what they mean there, but how could you make that clearer to the reader? We've talked a little bit about it, and how do you think you could do it?
You could say something like the calculated flow versus the recorded flow.
Yeah, or you could say flow meter. You could say something like precision flow meter on the left-hand side or something like that, and then flow from Bernoulli's equation on the right-hand side rather than theoretical. It's always kind of hard when you say theoretical, but that's why I think where you can have the slide really help you is that you say, you just put a little arrow here, right? Or listed over here, Q is from precision flow meter. Right-hand side, right, is from measurements around each obstruction meter or each, you know, the pitot tube, rotometer, things like that. So you can use the slide to help make sure it's clear where everything's coming from in the equation, rather than relying on theoretical. Or if you would have over here said theoretical, you know, is this hand side of the equation, actual is the left-hand side, right? Use a little arrow and use those same words on actual and theoretical so that you can see which one's which over here in your equation. This is a little weird. When I brought this up, it's kind of got a slide plus some extra stuff out in the no man's land of the slide. Okay. Any thoughts on this? Let's start with the topic sentence and the text. Anyone confused?
The topic sentence seems to like really only do half of it, but it's still like it's not terribly descriptive.
Yeah, we probably want to get calibrated. And in terms of the assignment or the purpose, you might want to say, right, we need to place new flow meters in our plant, and we've been tasked with testing the accuracy of the flow meters, or calibrating them and testing the accuracy of the options, something like that. What do you kind of like about the second line? At least the approach they're taking, but how could it be improved?
Sorry, before we move on, am I misremembering what the prompt actually was? Because I don't remember there being any discussion of there being a plant or new flow meters or anything. I just remember it saying test the ones we have.
Let me bring that up. Keep thinking about this and let's talk about that, and let me bring up exactly what we said, because maybe I'm remembering it wrong. Any other thoughts on the Yeah, I think isn't this kind of the prompt we had? A plan under development uses air various flows and the measurements of the flow rates of air needed to control the process. And then we want to not use turbine design or paddle wheels. So here's kind of the big thing, right? Calibrate each meter and determine which flow meter is most accurate.
Gotcha. I guess I just kind of keyed in on the last sentence of the first paragraph, talking about what was already in the lab. Okay.
So as I'm reading just briefly through this one, I think I like that you're trying to say that we have a mass flow meter, not necessarily as a baseline, but as a standard. You could say standard or a calibrated standard that we can use to calibrate, probably want to say an accurate standard that we can use to calibrate the other flow meters, something like that. But I like that you're trying to identify that the mass flow meter corresponds to the standard or the left-hand side of the equation. And then using a mass balance and a measured pressure drop. So the nice thing about this, the mass balance, it's not clear why you're using that. It might be better to say something like, right, obstruction meters or meters of this type are analyzed using Bernoulli's equation. Bernoulli's equation came from a mass balance, and then if you put Bernoulli's equation over here, then it's probably a little easier to understand. But I do like that you say, it's related to the pressure drop. And then I probably would stop the sentence after, explaining that the obstruction type meters are analyzed using Bernoulli's equation. And then you can refer to the slide, something like that, right? And say, the actual or standard flow rate can be related to what Bernoulli's equation produces by a discharge coefficient that we can determine, something like that. Let's go to the slide for a minute and tell me what you like, what you don't like.
There's too much going on.
Yeah, I think there's a lot going on here. I like that you identify a lot of the stuff, but you don't need to identify it 3 times, like Q is volumetric flow rate, things like that. Another thing for this type of slide, I think you could probably lump Venturi orifice nozzle and pitot tube together because it's very similar what's going on here. Or at least kind of group them all together when you're defining the equation or the variables that go in the equation. So I could save all this space here by just kind of pushing these over here and say Q pitot or Q other. And then you also, there's a little weird thing, right? Q actual versus Q gauge. All these Qs are actually the same Q on the left-hand side of the equation. So you want to keep that consistent. What are some other things? Is it easy to link the text to the slide? Do you know why the slide's there?
I mean, the last sentence of the paragraph says why the slide is there.
Yeah, the balance equations for calibrating each flow meter. I think, this gives you the link, but I think you can be better, right? You want to get people to the slide and make sure they understand why it's there, right? That I'm trying to get a CD value. This is going to explain how you're going to get a CD value. And I don't think the slide quite does that. I guess the balance equations don't mean much to me if you don't tell me how to use them. Okay, let's do the last one. And then, where did it go? Okay, we've seen this slide before, so tell me about the text. What do you think about the topic sentence? I think there's a lot to like about this text. It seemed pretty easy to read, but I think there's a couple things we could improve. What makes the topic sentence a little hard to understand? Any ideas? And it actually kind of works with the rest of the sentence, but right, propose an experiment to calibrate and determine which flow meter is most accurate based on Bernoulli equation. As soon as you put this in, then you've kind of elevated this whole sentence, and you got to make sure the rest of the text and the slide are related to Bernoulli. If you put Bernoulli in a separate sentence, you could say something like, right, 4 of the 5 flow meters we have are based on Bernoulli's equation. All of them we need to determine a discharge coefficient for, or something like that. And the equations relating, I do like, right, that it says, because we know the mass flow rate is constituted by, okay, this sentence doesn't, I like these, I like it from here. These data along with density of the pipe input in Bernoulli's equation to find a theoretical flow rate. So I think right here we could just be a little clearer all through here and say, right, we have an apparatus where each flow meter is placed in series. Because if you haven't told me that, you're kind of assuming I already know what the apparatus looks like, right? Because we know the mass flow rate constant through the pipe. That's assuming I already know that you have a pipe with all these flow meters in them. Does that make sense? Kind of assumed a lot already. You might want to just tell the reader that we have an apparatus where each flow meter is placed in series, and we can measure the pressure drops across each meter and also obtain the flow meter or the flow rate from the precision flow meter. by using the Bernoulli's equation, we calculate a theoretical flow rate based on the pressure drops, and then we can compare this to the actual or real flow rate from the flow meter and determine the CD values. And then you kind of go over here, say the slide shows you an equation that says, that relates the calculated flow from Bernoulli's equation on the right-hand side to the standard on the left-hand side, something like that. So I think the bigger problem here is, one, it assumes the reader kind of knows a lot already about the apparatus right here. And then two, you want to make sure that the text gets you over to the slide, and that the slide is working with the text.
So
okay.
When we're trying to find that balance of what the reader would already know, what they don't know, like, how do we find that line? Because I guess I assume we would be writing to someone who already was familiar with the setup, and we were just telling them what we were going to do.
I think,
like, so I guess obviously it depends on the actual person in real life.
Yeah, so I was taking the approach that, right, you just have got these flow meters from a vendor, and you've got to figure out how you want to do that. So there's no apparatus that's built yet, or something like that. Does that make sense?
Yeah, it makes sense.
I also have a question, Dr. Knotts.
Yeah.
So this is my team slide, and I was just wondering, you mentioned earlier that each meter will have a correction factor, and so it's not necessarily whichever one is closest to 1, because as long as it's calibrated,
that's right,
it shouldn't make a difference. So how can we adjust this, or what we've said, in order to state how we will choose which meter is the most accurate?
So I think we said that a little earlier. I think what you want to say is, once we calibrate them, you want to leave it a little open, say something like, we can assess the accuracy across all the flow rates to determine which flow meter to install. Because just because you have a CD value doesn't mean that it's accurate at low flow rates versus high flow rates versus medium flow rates. Does that make sense? You might be off at high flow rates. You might have one meter that's accurate across all the flow rates to like 5%, but you might have a meter that's accurate in the middle flow rates to 1%, but is really bad at high flow rates. Maybe it's 10% off. So all that goes into your decision. And I would just say something like, once we've calibrated them, we can look at the accuracy across the flow rates and determine which we want to select. Something like that.
Okay, thank you.